This lecture is, the title is Creative Driven by R&D. And before I started this lecture, I would like to thank Kamuda for inviting me to open my solo show here in Zurich. It's actually would be my first solo show in Europe, which is quite an honor. So first, a little background about myself. I'm a visual artist, animator, and creative technologist, or you can just call me programmer, would be sufficient. I graduated from Rensselaer Polytechnic Institute with a Master of Fine Arts degree back in 2014. And my artistic and research interests mainly focus on exploring visual aesthetics brought by customized computer algorithm and software process. Processing is the tool I use for many of my personal and collaborative projects, but I'll actually show you the software and the IDE in the lecture, so don't need to worry if you have no idea about what processing is. For this presentation, I will not dive too much into technical aspects. There will be some nerdy parts, but not that much. I'm going to start from like one experimental, playful little sketch I randomly put together a couple years ago, then track all its derivatives branching off from this little sketch, basically showing how I push a simple idea from like an R&D project and how I push it in multiple direction and how to merge that idea with something seemingly irrelevant into something more complex and more rich. So in November 2016, I think, I randomly started a casual research into KD tree. And yes, I can often do that type of thing when I don't have like a marching deadline. So sometimes the research is about data structure, sometimes it's about algorithm, just things that can potentially be implemented in code and can be visualized in potentially in an aesthetic way. And I have this brief definition of KD tree created from Wikipedia. So KD tree, D basically means dimensional. It's a K-dimensional tree is a space partitioned data structure for organizing points in a K-dimensional space. It might sound a little bit abstract, so KD tree is widely used in range searches and nearest neighbor searches in the field of computer science, but for me, I'm more interested in exploring its aesthetic potential. So this is the first rough demo. So for example, we have a space here. Whenever I click, it would subdivide the corresponding area. And you can see there are like small digits along the vertex of each rectangle, basically implying the interpolation of that current node. It's actually in like a percentage manner. So like it's like, for example, this point is 1174, so its X position is basically 11 out of 100, and its Y position is 74 out of 100. And I kind of added like some little physics simulation to it just to make it kind of jelly-like elastic. Okay, later in mid-December, I extended the exact same principle into a three-dimensional. So the square is replaced by like a cubic cell, and the z-axis is integrated. You can see there's another z-axis going in like a diagonal manner here. And I'll show you the video demo, and you can see the digit is highlighted in purple. So it's basically the exact same principle, but since we add one dimension to it, it just gets more complicated. So in this demo, you can basically roaming around the 3D space, and it would randomly pick a cell and keeps subdividing it. Yeah, so basically the square is replaced by a cube, and the rest remains kind of identical. Exact same principle. Yeah, I also tried messing around with the principles a little bit. Generating splits that ain't necessarily parallel with the corresponding axes using unequal interpolation percentages. So I'm gonna show the video and I'll explain it at the same time. So you can see I'm assigning each node with a slightly different interpolation value. So it's kind of creating 4 colliding planes with each split. Everything is not like perfectly aligned, but it's kind of interesting. It kind of makes the tree more distorted and chaotic, and also sets a foothold for a few projects I'm going to talk about in later part of the lecture. So yeah, this is like a skewed version of the 3D extension demo. So Christmas Eve, apparently I had no better things to do, so I implemented some shifting interpolation on every level of the 2D tree. So in this time, instead of using a global percentage, I'm kind of using I'm assigning a local interpolation value. So if you still remember the coordinate on each node, this time I'm using kind of like a relative value. So it's basically the value is depending on the position based on its parental unit. So instead of on a global level, it's kind of more on a local level. It's a little bit hard to, it's a bit abstract, so I'm just going to play the video. Yeah. So by changing the interpolation value on each level, I can kind of control the pattern. And if I set all the values to like 0.5, which is right in the middle, it can become like a real formal grid. And in this demo, you can see the interpolation value is kind of randomized after a certain period of time, and it kind of forms into a loop. Yeah, just different kind of direction, trying to play around with the KD tree structure. Yeah, so although each subspace from a 2D tree has like 4 vertices to define its boundary for visualizing purposes, however, I don't have to connect all of them into like a standard rectangle, right? We can also like connect them differently just to make to create like a different kind of visual texture. So this leads to the next demo by using a different vertices interpretation. So there's a function in processing called begin shape. And it's kind of similar to the GL begin open GL. It takes one parameter, but can completely change how the vertices are interpreted for the program. And it can specify the different type of primitives to be created. So basically, I merely change one parameter. Yeah, I'll just play the video at the same time so we can see the difference. It's basically the exact same principle, but I kind of change how these vertices kind of connected, so it kind of has a different visual texture. I mean, this one specifically looks like kind of like a recursive dragon curve form, kind of. So yeah, just by changing one parameters in the previous demo, I got this result. I think this is also one of the many charms of processing and other creative programming tool. Just changing one parameters, get a totally different result. And this is just a comparison of the exact same animation loop, but with a different kind of vertices interpretation. You can see I'm assigning the exact same like interpolation pattern to the left and right, but still, it's kind of interesting. And this shifting interpolation mechanism also works in 3D as well. And you might notice that I changed the animation of this structure a little bit. Let me just play it. I kind of removed the like elastic ones just so it doesn't get too hectic. So basically adding one dimension, and the visual kind of gets real complex with the elevation of the recursion level. But you can see there, it still has this kind of similar like features when I kind of assign all the interpolation value to 0.5, and you get like a really ordered, organized 3D grid. So besides geometric line segments, I also started to think about the possibility of using KD tree to represent non-abstract objects. So first thing came to mind was to do it through texture wrap and kind of bounding each cell vertices with a series of UV sets. And okay, the test subject I used was one of my favorites, the Dodge, right? Seriously, who doesn't like it? So I'm going to play the video as well. I can't explain it. So to avoid too much texture mapping artifact, I kind of limit the interpolation range on purpose so it doesn't get too kind of, you're not getting a really squashed dog face. Plus you can see that the entire tree is triangulated, just so like all the faces I have is like a triangular face. And by animating the KD tree, I can make the Dodge kind of make some funny faces. But this is one way of using KD tree structure to present non-abstract object. But what about without using the texture? By changing length, weight, density, distribution, etc., it is also feasible to use simple geometric shapes like dots, lines, and grid to represent non-abstract objects. So the same applies to KD tree. I just need to figure out the best way to kind of create a mapping from the non-abstract object data to the KD tree structure parameters. And I'm going to show you a few of my experiments. So the first experiment is topography. Okay. So each letter is kind of rasterized into a bitmap, and the split of each cell is positioned at the darkest column or rows of pixels within the cell. And by switching letters, a new set of interpolation values could be assigned to the KD tree, so just making this type of quite smooth transformation. It's not like super recognizable, but it's just like an experimental direction I chose to go for. And it can not only work on singular letter, it can work on like multiple letters, and using a transformation on the word as well. And this leads to the next demo. It's a text pattern mapping on multiple letters. You can see it's getting kind of quite hectic, but the transformation is also interesting to look at. Yeah. This animation kind of actually like all the KD tree cell doesn't kind of animate at the exact same time. I kind of differentiate the animation based on their recursion level. So the lower recursion level kind of do the transformation earlier than the cells on the higher recursion level. And it applies on different type of text as well, since all texts are kind of rasterized into images, so it doesn't really matter what language or what type of text it uses, or whatever typeface. You can see the hello is slowly, gradually transforming into word. And in case you're wondering what the Mandarin characters is, it's basically Chinese in hello world. So 你好世界 here. Yeah, it's not extremely decipherable, but personally I still find it quite intriguing. It has a certain type of futuristic and almost like a cyberpunk vibe to it. Okay. Yeah, then next demo is something pretty recent. I mean, it's still last year, but it's like relatively recent. So it's a KD tree digital clock, and this one actually going to be real time. So I'm going to change the setting on my computer and make it like a duplicate mode. Yeah, so this is actually like a randomized KD tree, and the color is kind of randomly assigned as well. But I can kind of change its interpolation value and randomize its color. And I can also reset all the interpolation value to 0.5, and at the meanwhile, I'll also assign like a smooth gradient color. So get a smooth color. Yeah, but I mentioned it's a clock, right? I can use this to display some digits. So I think I should press 3. Yeah. So I got hour, minute, and seconds. And their position is kind of related to like the digit is like 60 would probably be at the bottom of the right tile. And when it reaches 60, the middle tile would kind of change. See that? Yeah, so it becomes like a digital clock. But the principle, the mathematical principle behind this clock is basically a KD tree structure, which is a data structure in computer science field. So yeah, it kind of looks like a glitched screen a little bit, but still, I mean, I find it beautiful. So the second experiment is carried on my own face, and I used OpenCV's face tracking feature to generate a KD tree attached to my facial area. I'll just play the video here. Yeah, but you can see here. So the way how the tree is subdivided is basically is the same as the topography experiment, since my face is also treated as a bitmap, and each cell split at a column or row of pixels that has the lowest brightness. And I also mapped the position of the rectangle with the position of my face within the image. So it's kind of corresponding. And here's another demo using the previous pseudo dragon curve mode I just talked about earlier. But let me show you the video. This one is kind of more, the transformation is more kind of smooth. But yeah, it's still based on the exact same principle with a different vertex interpretation. In late 2018, I combined both texture wrap and interpolation map into a hybrid. So unlike the previous dog experiment, I didn't use an image of the exact object itself, but a black and white half-tone pattern. And let me show you the video. So for a half-tone pattern, this kind of like a stripe pattern is called a kernel. So by changing the kernel's UV coordinates, I can control both the frequency and the spatial filtering of the pattern to better fit an area of pixels. So as you can see, the outcome is way more identifiable even at a low recursion level. And here's a more fancier version with a different radiant half-tone pattern. And I also add some displacement along z-axis, so it's basically 3D. Still mapping my face, but kind of added like a height map effect to the structure. So it created this kind of depth, but it still is using a KD tree structure. Next, I'm going to talk about mixing KD tree structure with something seemingly irrelevant. If you're into generative art, you might know a little about something called a vector field. To put it simple, it's a collection of, you can consider it as a collection of arrows, and each has a certain direction and magnitude. And many digital artists harness the feature of vector field to do in their works, and by placing tons of particles within the vector field and all the particles can be collectively driven by these arrows as forces, and leaving a series of beautiful trails in the process. So I know it sounds like something completely different from a KD tree structure, but we can still kind of mix them together to get some interesting results. For example, what if I customize the initial starting point of all particles, and what if I create my own vector field with customized gravity points and kind of bound those points to the KD tree structure? And I got some interesting results from this idea. These are like KD tree, but with the integration of vector field in 2D. And I'll show you the animated results of this experiment. Might looks a little chaotic, but you can still tell the rectangular boundary of the KD tree cell. So basically by placing these particles along the boundary of the cells, you can get these interesting results. By feeding different parameters to the vector field, the results can vary based on these parameters. So the same thing can be applied to a 3D tree to get an even more rich and complex texture. I'm going to play the video. You can still barely see the like a reddish contour of the KD tree cell in these cuboids, right? It might be a bit hard to identify with, but yeah, this one's pretty computationally heavy. Took a lot of like rendering time to get the smooth animation like this. Okay, so this demo is going to be a little weird or interesting depending on your perspective. Okay, so I got all the windows, right? You see that? The neon cat actually consists of tons of windows, and they're actual windows. They're not like fake windows or visual effect. They're actual windows, right? And I actually have a control panel to control the playback speed of the cat. Right? Go crazy on that or go real metal. So yeah, you can play around with windows a lot instead of like just drawing geometric shape on one window. Right? You can actually use window as a texture or as like a paintbrush. But yeah, it's quite fun. And actually I have another exact same cat, but the slider kind of do a different thing, kind of makes the cat a bit fatter. Again, check. So, yeah, the width and height of the rectangle is kind of calculated to make a constant area of the windows. And yeah, so basically for this demo, I mapped the tree's rectangular cells properties to a group of windows, and more specifically, the window's top left position, width, and height. And we'll play the video first. So you can see the color palette apparently inspired by the Dutch abstract painter Mondrian. And there's no specific motivation behind this piece. I'm just trying to do some random experiment. But I kind of wonder if the painting was aware of the structural principle behind his own works. So it's quite like a totally different perspective from like a mathematical point of view. So we can actually take a break for now. If you guys want a break? Okay, yeah, let's take a break. Like 5 minutes.
Yeah, perfect.
So moving on to yet another derivative, I was doing a casual research into fast algorithm for array triangular intersection, and I put together some demos to test its performance enhancement. So basically, let me play the video of these experiments first. So basically, these experiments use the 6 faces of a cuboid cell because it's a 3D tree, right? So each KD tree cell is like a cube which has 6 faces. So it uses 6 faces as a clipping plane to clip off each cells containing geometric objects. For example, the top left corner, that demo is basically a grid of diagonal lines, and the one on the right is a pile of circular rings, but by assigning each group within a specific containing cell with a different rotation angle, it kind of creates this type of fragmental visual effect. The second row contains a layer of characters. But basically, these characters are broken into tiny line segments. So the implementation, from an implementation perspective, it's not that much different from the first row. So I kind of personally find the geometric contents orientation reset is satisfying to watch. You see that split second when everything becomes together again. Like that restoration process kind of quite satisfying to watch. But yeah, like this one, still based on KD tree, but the KD tree cell is not visible, but you can still tell from these containing geometric objects. Next, I'm going to talk about the development of a piece of mine named the Autotroph. This piece I'm actually going to present here at Muda, but in like a physical form. It actually has a few digital predecessors that combine elements in many of the experiments I mentioned earlier. But first, a couple of experiments as foothold. So let me play the video and simultaneously do the explanation. You can see there's still KD tree, but I just added 2 additional like tangent shapes into each cell. Plus, I added some round corners for the cell boundary, and you can tell it has certain like organic motion pattern, which is driven by my favorite, purling noise. And yeah, by combining these features together, it almost giving it like a lifelike texture. It almost feels like the KD tree is kind of breathing some way. So these 2D experiments were eventually revised and improved into a more formal piece, and I named the piece Autotroph. It's created 2 years ago. And it was especially built for a digital art platform called The Frame. It's a Japanese, it used to be a pretty popular Kickstarter project back in the days. And I also made a breakdown video to explain both its features and my process. Again, I will play the video, but you might recall some of the experiments I talked about earlier in this lecture. And they're pretty self-explanatory, but I'll make some comments with the video. So it all starts with like a very simple, basic KD tree subdivision. And you can assign each split with a different interpolation value, which create this kind of distorted, skewed visual effect. I resetted the cell. And to create a cellular structure, you're adding these interpolation points along the boundary. Like if you do it twice, you get a pretty smooth boundary. And you can also interpolate all the vertices in like a radial manner. So it kind of gets like a cell-like visual effect. And you can add these little cells into a KD tree structure. By changing the radial interpolation, you can get like a smoother transformation animation. Also, you can assign the weight of each cell. like the changing of a certain cell's weight can affect its neighboring cells as well. And this process can become autonomous as well to make it more like just like its title, Autotroph, right? An organism grow on itself. I think I speeded up the process a little bit just so we don't have to wait in half an hour to to see how it looks like. And yeah, since it's developed for Frame, Frame actually has like an integrated video camera, so I added some subtle interaction to it. Basically, it can detect your like a motion level through a web camera. Basically, it's like how many pixels are kind of different from its previous state. So this way, I can detect like if the audience is kind of moving right in front of the camera, so it can create some type of like a morphing. It also has a day and night mechanism, kind of similar to a plant. So yeah, that's like a breakdown video I put together 2 years ago, I think. But yeah, you can recall I talked a lot. I kind of break down these little features throughout the entire lecture. So it's kind of everything kind of come up together. So I built another customized version for. There was another customized version of Autotroph for a Dawn gallery in Taipei City early last year. And this is for this super long tile of LED wall. And there's a video I made. Yeah, this one is, it doesn't have interaction. It's basically like a rendered out video kind of looping on this super long tile of LED screen on the streets of Taipei. A really short video, just to show you some different variation of the work. Yeah, so last year I also did my first solo exhibition in China, which had a quite small but pretty interesting art gallery in Chengdu. And I customized the Autotroph for the exhibition, and it actually would take the organism would split based on the webcam image it took from the audience. So actually, I think I can demo this version in real time. Probably gonna see my huge face on the screen. Yeah, let's see if it, taking the image. It takes some time for it to capture the image. And the cell kind of keeps splitting, and you will eventually see my face like emerge from all the cell pattern. Can probably tell somehow already, but can see it, right? Yeah. But yeah, after a certain period of time, the cells would kind of merge back to like original KD tree. It also interact with my motion a little bit. It gets a bit jitter on my computer. I'm not exactly sure why. Probably it's running on 4K, that's why. But yeah, let's just wait for a few more seconds, and it will merge back to its original states. And like after every like a minute or so, it would just start capturing another image and feed itself to generate a different pattern. So that's how it works. So in mid-October 2017, these creature-like characteristics were fused into the 3D version as well. So I think you might start to discover a pattern here of me rehashing my own code, like doing 2D, then extend it to a 3-dimensional, just test with different variation. It's kind of not that original in some way, just kind of 2D, then 3D, right? But yeah, so these are the like the 3D organic motion of the KD tree. And the first demonstrates the subdivided cube created through like a skewed version or the distorted version of the split plan. Like I mentioned, I can assign the 4 different nodes with like a slightly different interpolation value. If you still recall the 3D KD tree split demo I showed right around the start of this presentation. And for the second one, I can interpolate each cell between its own boundary, a cuboid, and its geometric center. So you can see there is some gap between each cell. And for the third one, I kind of replace each cuboid cell with an internally tangent ellipsoid. So almost the same principle, but just some different parameter set and a little personal touch, I would say. So this further leads to a prototype of the Autotroph 2.0, which is the same Autotroph, but in 3D. Not very creative, but it kind of looks good. So this is a prototype of the Autotroph 2.0. It's just like a looped animation, basically the same aesthetics with the original Autotroph prototype. Yeah, for the next one, I added more kind of split process, also the weight assignment process. But this is simply a prototype, and I have a second prototype. So this is a second prototype, like a video demo showing the dynamic subdivision process, plus some weight assignment of each cell. It's similar to the mechanism in the breakdown video of the original Autotroph, but just in 3D. You can still click a certain cell, and that cell would keep further subdividing. Okay. And the piece eventually lead to Autotroph 2.0 itself. And the Autotroph 2.0 is, I think it was premiered last year at the Xi'an Gallery in Washington, like around January or so, right after the PCD event. And I'll just show you like a section of it, since the entire process would last for about like 8 minutes or so. But I'm just gonna show you the real sweet part, which where like all the cells kind of subdividing and showing the complexity. Also changing the meshing for this a little bit. Instead of just drawing a rectangle, I'm using like a diagonal line to wrap around each cell. So yeah, that's a segment of the Autotroph 2.0. So in mid last year, not last year, it's 2 years ago. Yeah, mid 2018, I collaborated with a British electronic music producer named Max Cooper on a generative music video project named Rule 110. The sound has the exact same title. Rule 110 is actually a rule for elementary cellular automaton if you're into computer science. So I I adapted the piece into a three-screen environment a year later for the New Media Art Festival in Shenzhen. So the entire video is one continuous shot showing the granular evolution of an elementary cellular automaton traveling through a tunnel. And if you pay attention to the tunnel walls, you can notice that the wall consists of a long tile of KD trees. And here I'm just going to show the original music video. The original music video used an orthogonal projection matrix, but for the show here at Muda, I'm actually using a perspective view. So it kind of looks different, but yeah. But the version shown at Muda actually would be an enhanced version of the original video. So. You can pay a little attention to the tunnel wall, and you can see the texture of the KD tree. See that? It's actually like a division. Oops, sorry. Good. So this is kind of a project. I kind of put the experiment kind of into like a formal big project. So I want to point out that KD tree doesn't have to subdivide a space in a Cartesian coordination system. So this leads to the next derivative I'm going to show you, a KD tree applied to on a spherical surface. So we are going, going even more complicated, going non-Euclidean. So apart from being parallel with x, y, or z axis, the split can also kind of line either on a polar angle or theta or azimuthal angle, or so, aka phi in a two-dimensional polar coordination system. And with the theta range from 0 to pi and phi range from 0 to 2 pi. So this is a diagram I draw just to explain a split on a spherical surface still using the KD tree principle. So actually this sphere is first divided using by point A. It has still has like two different value. One is along theta, and the second is along with pi. And actually, I can play a video. It might be a little hard to tell when, because I cannot actually draw the fragment of each KD tree cell, because it would be like computationally expensive to draw, because each fragment would be like a how do I describe it? Like as long as it's on like a curved surface, it becomes complicated. So I kind of just only draw in this demo, I only draw the edge on each cell. But also with each split kind of assigned with 0.5 value, it kind of become like a average distributed sphere visually. So I also play around with different radius displacement, mapping each fragment's interpolation to its visibility, and I got some quite interesting results. It's kind of like the second demo of my half-tone pattern. Basically, you're adding for the half-tone pattern, I'm basically adding like a z displacement for each KD tree cell. But for this demo, I simply add like a displacement along the radius of that sphere, and created this kind of fragmental collective of geometric shape. So in late 2017, I adapted this demo for a collaborative project with Symmetry Labs. They're a San Francisco-based studio doing large-scale LED installation. So they built a public art installation at the Seaport District in New York City, and I produced some of the visual content for their customized LED. And this is the final result with all the pixels calibrated. And sorry, it's third time. We have to put like a diffusion acrylic shell right outside of the LED screen, because the weather in NYC in winter isn't really that nice. The snow can destroy all the hardware hidden within the LED screen. So the shell kind of makes the visual content less crispy, but it is, like I mentioned, it is kind of necessary to keep the inner hardware away from the harsh winter. These are some different patterns, because it's kind of like a mix added, so you can only see part of the KD tree pattern. They're actually interactive. And we put some like a thermal camera on top of the roof on the surrounding building, so they can pick up where the pedestrians are at, and the image on the LED screen can change accordingly with their position. I'll just stop the video for a minute. definitely put the feasibility study into good use. And last year I collaborated with a Hangzhou-based sound artist, Wang Zhehui, and his artist alias is Valley, and made this collaborative audiovisual piece. I named it 18093. It's like I actually just turned the data of its prototype into a hex number, so that's how I got the name. It's just like a lazy way to come up with a name. I was so bad at coming up with names. So it originally served as a performance for Westbound Museum, the ex-Central Pompidou project, opening night in Shanghai, China. And it was a pretty recent project, like a few months ago. So this project was further revised earlier this year and adapted for an immersive triple wall setup for the mood I show it here. So it's actually would be the premiere of this show's immersive triple wall version here at Muda. So yeah, again, come by and check it out during the opening. And here I'm just going to play the documentary, a video of the performance at Westbound Museum, and we can save the best for during the opening. Yeah, the setup is a little unique because we have a huge projection on the floor, and at the same time we're using a live video camera to capture from like an area view and projected that real-time camera feed onto the front screen. So it's you can see the front screen. You can actually see the audience kind of stand on the projection. the last part to kind of go a little dizzy, but you'll feel even more dizzy during your experience at Moodle. So yeah, that's everything I have for this lecture. So I know the timeline might be a bit. Yeah. Thanks, guys. Thank you. So I know the timeline is a little confusing and messed up, but I didn't exactly do this in a chronological order. You can see all the dates I put with the work, and it's not really in a very good order. But even after I catalog these experiments based on their visual styles or implementation methods, it's still quite hard for me to prepare this presentation, because for the presentation, I can only do this in a linear way, so it's kind of becomes tricky. But I mean, I just hope the lecture has been informative and you guys enjoy it.